Well, good evening. Welcome to the Royal Society. My name is Russell Foster, and I chair the Royal Society Public Engagement Committee. It's one of 4 committees that report directly to Council. The President of the Royal Society, Sir Paul Nurse, has asked me to deputise for him on this occasion, and he expresses his profound regrets that he can't be with us this evening and wishes our speaker the very, very best. Before I begin, we've got to do some housekeeping functions. Could I ask everybody to ensure that their mobile phones are off? Actually, I'm not sure where mine is. That the fire exit is that one over there. And if you hear an alarm, it will not be a test, it's the real thing. So move slowly and orderly to the fire alarm. And also to remind you that this event is being webcast and recorded. Well, as you can see, tonight's presentation is entitled, Is Chemistry Really So Difficult? And it's being given by Professor Andrea Sella, who is, of course, the winner of the 2014 Royal Society Michael Faraday Prize. It occurs to me, before we go any further, there's a question. Is chemistry really so difficult? So, a showing of hands here. Who finds chemistry difficult? Well, that's a relief. So, Andrea, you've got some convincing to do this evening. A little bit of background on the Michael Faraday Prize. It's awarded annually for excellence in science communication, and it recognises a scientist or an engineer whose expertise in communicating scientific ideas to the broader community is truly outstanding. And as you'll see, Andrea certainly fits the bill there. Recent winners of the Michael Faraday Prize have been Jim Al-Khalili, who is sitting over there, the late and great Colin Pillinger, Jocelyn Bell Burnell. I don't know if Jocelyn is here this evening. If any of you are here, please wave. Marcus de Sortoy, Brian Cox, and last year, of course, it was Frank Close, Professor Frank. Frank is here. Excellent. A little bit of background about Andrea. He is a professor of inorganic chemistry, and he's based at University College London. He gained his PhD in inorganic chemistry from Oxford, and I'm very pleased to see that his mentor, Professor Malcolm Green, is actually here this evening. So welcome, Professor Green. And has been at UCL since 1990. Now, Professor Sella has been involved in communicating science to the broader public through numerous radio and television productions, and was nominated for a BAFTA in 2010. You must be the only scientist ever to be nominated for a BAFTA, which I think is extraordinary. Oh, really? Oh, I see. And he currently contributes to the BBC World Service business series, The Elements, and writes a monthly classic kit column for Chemistry World. Now, sort of from a personal note, it really is a particular pleasure to be able to introduce Andrea to you this evening. I've got to know Andrea through the Cheltenham Science Festival, where he's been a major and star contributor for many, many years. Andrea is not only a brilliant communicator, as you'll see, but he also generates genuine warmth. And I mean from other people, not from the explosions he sort of sets off. Indeed, when the community knew that I was going to introduce Andrea this evening, I was flooded with stories about him. And I've been told to keep this brief, but I've got 3 very brief quotes that I thought I'd share with you. The first is actually from Jim, who's sitting over there. And the quote was, "In my BBC programme, Chemistry, A Volatile History, Andrea was a major contributor. The best part," I'm assuming that's the best part of the whole series, was it? Yeah. "The best part was probably when we were discussing alchemy, and he boiled up some of his own urine that he collected in a Coke bottle. He even made me sniff it." And Jim goes on to say, "It was very unpleasant." But Andrea seemed pleased with my response. Then we have a wonderful quote from Mark Majadovnik, and I think Mark is in the audience here. Yes, there's Mark. And this is a lovely quote, and he said, "I happen to know that Andrea has been a body double for Professor Brian Cox in his latest series. I only know for certain about him being a double for Brian's hands for some of the demos, but," Mark went on to muse, "it could be that some of the long shots of Brian on a mountain waving at the helicopter were also Andrea in a wig. The Royal Society needs to know." So that's probably the first question we'll ask you when you've finished. And then finally, from the inimitable Quentin Cooper, and this is a lovely quote again, "Whenever I've worked with or seen Andrea, he has invariably turned up with cases, vials, cylinders, armfuls of often dangerous chemicals, but always something isn't there, or it's disappeared en route, or broken in transit. This only serves to fuel the manic chemistry on the edge vibe that always makes you feel, when watching Andrea, that there's a 99% chance of enlightenment and a 1% chance of being set alight. Ladies and gentlemen, it really is a great privilege for me to be able to present Professor Andrea Sella to deliver the Royal Society Michael Faraday Prize. Andrea.
Thank you, Russell, and thank you all for coming tonight. And true to form, I did have this panic in the last 15 minutes. I suddenly started thinking, where are my safety glasses? They're there, fortunately, so it's okay. I'm delighted, I'm honored, and I must say, I think I'm more surprised I'm just so surprised to be standing here to receive this prize. And really, let me just tell you, imposter syndrome spares no one, right? The others who've stood on the stage, who've had this prize before me, are all people who've been real inspirations over the years, and it was an incredible pleasure to meet Richard Dawkins earlier, and just to remember that my father, when I was 16, gave me a copy of The Selfish Gene when I was a teenager. And you know, I've read their books, I've watched their teleprograms, I've seen their lectures, and I can only say that if I've got here, I think it's by crawling between the legs of giants. Now, you know, I have to thank Russell and the panel for choosing me, but alongside them, I'd also like to change some people who completely changed my life. And that was the panel of the EPSRC Senior Media Fellowship, it's a kind of exciting title, that include Deborah Cohen of the BBC and Robert Winston. And what they did was they gave me more time to talk about chemistry. And what they did was not only change my life in terms of kind of how I talked about chemistry or whatever, but they also changed all of my friends, right? And the best thing is that they opened the doors to a whole pile of people whom I never imagined I would ever meet before, and it's been great. You know, there's also Malcolm Green, and Malcolm Green was my mentor, as Russell said, when I was a graduate student. And he gave me, I think, what I'd like to call a sort of thoughtfully fearless attitude to chemistry. And he's the reason why I have distilled urine. I still distill white phosphorus and stuff like that. But years ago, he asked me to talk to prospective undergraduate students. And Peter Scott, who is somewhere in the audience, will probably remember when we used to flick little bits of alkyl lithium, sodium, potassium fragments out of a flask across the lab, and they would sail across with these beautiful, either pink or lilac or yellow flames. It was quite amazing. But it kind of got me started. And then at UCL, of course, you know, it's been incredibly nice to have colleagues who've actually encouraged me to do what I do, but especially Graham Hogarth and Steve Price, with whom I used to do double acts, you know, a very long time ago, and who taught me enormous amounts of chemistry. But they also had the grace to tell me that I'd probably gone a little bit too far this time or something like that. And on the other hand, let me just say that Jim Al-Khalili, Mark Miodovnik, and Stefan Gates have done precisely the opposite. So, and finally, there are really two crucial people that cannot go unmentioned. And there are two senior lab technicians, Crosby Medley and Phil Hayes, who over the years have prepared solutions, made liquid oxygen, lent me weird glassware at short notice, and so on, and dealt with my mess. And that's something that I think my family can appreciate. You know, thank you, because without you guys, I would never have been able to do what I've done. Now, as I look out across the audience tonight and see so many friends, I feel as if I were at one of those meetings where you're supposed to say, my name is Sella, and I'm a chemist. And that's partly because, of course, I am totally addicted to chemistry, but also because I've got a huge chip on my shoulder about the subject. And the reason is, I think, because very often when I say that I'm a chemist, people say to me, oh my God, I hated chemistry. It was so hard. It was awful. I was terrible at it. And I'm never quite sure how I'm supposed to respond. right? I mean, if you tell me that you're an accountant, what am I supposed to do? Am I supposed to say, oh, I always thought bean counting was a bit dull, or tax evasion, or I don't know. But I just kind of mutter something like, well, I'm really sorry that you have no idea what you actually missed, because I think chemistry is amazing. And on the other hand, there's a lot of people out there like Mark Lithgow and Frank Close who really expect me to, in the parlance, blow shit up, right? And so I think I should humor them by just doing just that right at the beginning, just so that we kind of get it out of the way and then we don't have to worry about it. And here is the point where the fact that I'm now old enough that I can't see anything and the fact that I have to wear safety glasses kind of comes into play. But what I'm going to do, Quentin Cooper says, I always turn up with a cylinder. Well, yes, I've got a hydrogen cylinder here. And I'm going to do a classic that you're probably all familiar with. We're going to take some hydrogen. We're going to blow it quite loudly around the place because I know you're all hoping I'm going to burn the building down. And what I'm going to do is I'm going to fill it from the bottom because it's less dense than air. Then we can fill from the bottom, it will fill up. And there's a little hole up at the top. And so like the little Dutch boy, I can put my finger in the dike up at the top, and eventually, are we sure it's full? Let's just check. Yeah, I think it'll do. Okay, and it's fine. And now, of course, what I need are matches, right? So what could possibly go wrong? So what I'm going to do is I'm going to light it at the top. Are you ready? And you hear a little pop, and I hope that some of you are pretty disappointed because there doesn't seem to be an awful lot going on, right? I mean, hydrogen is supposed to be this horrendously flammable stuff, and there's no flame. Well, actually, flames are usually because either you have molecules or particularly you have soot, little bits of hot soot that kind of dance around in the convection currents created by the temperature rise from the reaction. And actually, from my vantage point, where we've got these really good, very parallel lights, I can actually see that this thing is rather warm. In fact, I can feel the warmth up above. This thing is burning, but it's burning very, very cleanly. All we get is water, and this is the great promise of the hydrogen economy, is the idea that we would be able to burn things and actually not end up with any pollutants. But hang on, I can hear something. Oh. Kind of weird, right? Oh, it's dropping. This is getting kind of interesting. You can hear an oscillation. Oh, okay. Well, I've achieved exactly what I wanted to achieve, right? Is that, there's lots of laughter, there's applause, everybody looks at everybody else, people are smiling, right? Yeah, this is chemistry, isn't it? Okay. And chemists have spent almost 300 years doing this kind of stuff. And what I'd like to do is, if I've got this thing queued up, and of course I have it in the wrong place, so this is a bit of a problem. I don't know how I've managed to screw this up. This is quite typical. Let me just see if I can cue this. We're struggling for a moment. But we've spent about 300 years trying to impress people. My computer is now crashed. Trying to impress people basically by blowing stuff up. And you can read about, yes, indeed, we've crashed. So this is a problem. Let me just get this restarted. So much for any hopes I had of sticking to time, right? Now all bets are off. You're going to be here for the whole night. But we spent maybe 400 years trying to impress people in this way. And if you want, you can go and read a history of the chemical demonstration. And there's a wonderful book by Otto Kretz and Fritz Kreisel called Feuer und Flamme, Schall und Rauch. Fire and flame, bangs and smoke. It's a brilliant book. It combines the history of the demonstration with a compendium of really some of the most spectacular and dramatic of chemical reactions. And let me just see if I can show you the cover in a second. Okay, now I've reordered things. Let's just see if I can get this to work without it crashing. That would be a real bonus. Okay, there we are. Okay, so we have a slide here. And so, there it is. And, the sad thing about this book is that it's never actually been translated into English, and there's a little pet project for someone if they want. But to me, that title speaks volumes about the way we present our subject, and that is that it's exciting and that it's dangerous, right? And you know, the connections in the human psyche between fun and danger are established sometime around age 3, right? You know, that's when we first start getting into this stuff, is that, you know, the naughty, dangerous stuff is where the excitement lies. And so blowing stuff up is a fantastic way of getting people's attention. But you know, I'd argue this is pretty easy, right? I mean, blowing up a little can of hydrogen is really pretty straightforward, and kind of any monkey can set up a demo without too much trouble. My question is, if I've started out by blowing something up like that, you know, a tin of hydrogen, how do I follow it? What comes next? Do I blow up a bigger tin of hydrogen? Do I blow something up which has hydrogen and perhaps magnesium in it so that you actually get a flash? And at the end of it, particularly for the non-chemists, what message are you going to take home about this discipline? And you see, this reminds me of a lecture that I gave many years ago, and it was a very typical chemistry flashes and bangs lecture. And I just remember there was loads of laughter, there was loads of applause, but at the end of it, a colleague of mine came up to me, and he said, you know, that was really great, I really enjoyed that, but you know, there wasn't much of a theme, was there? And I was crushed, because I thought, of course there's a theme. It was about energy and transformation and chemistry, right? He was right. He was right. It was just kind of random nonsense, right? One thing turned blue, another thing blew up. And it was like one of those kind of classic videos from the World Cup, right? This sort of thing, the top 10 goals, right? You see the kind of highlights, but it doesn't actually tell you an awful lot about the discipline itself. And I think it kind of misrepresents our subject. And in some way, a lecture like that is the equivalent of kind of chemistry porn. You know, what we need to do, perhaps, is to change the perception. I mean, what's the perception that people get when they come away from a lecture like that? Well, the basic idea is that we're people who wear flak jackets, right? Helmets, ear protection, glasses, when we're actually in the lab. And more importantly, I think they leave out something really important, and that is to present chemistry as one of the towering intellectual achievements of our age, right? It's an extraordinary fact that over 300 years, 400, 500 years, there's been this methodical work by hundreds of often anonymous individuals, right? That has completely changed our worldview, our economic system, the way we build, the way we eat, the way we decorate. I mean, even the way we play. I mean, this one's for Robin Clark here at the front. Can you imagine playing a round of golf the old way, i.e. with a leather pouch stuffed with feathers? I mean, you know, it's an incredible tribute to polymer science, the fact that we have these extraordinary materials. And so my worry is that if we spend an hour simply blowing stuff up, then we're seen as purveyors of kind of cheap magic tricks, and we fail to convey the astonishing invisible world that lies just below the level of what we can perceive with our eyes or feel with our fingers. And at the same time, we undermine chemistry as a crowning intellectual achievement of our time. At the same time, we're also going to alienate a lot of people who think we're basically childish and dangerous. And I think that's a real worry for chemists. And potentially that's one of the sources of chemophobia. But that's only the beginning, right, of the misrepresentation. And I want to try and draw your attention to the fact that chemistry has largely changed. I want to tell you a little story about a friend of mine who I think is in the audience, and I'm not going to name her, but she's a senior television producer. And she asked me whether she could pick my brains about interesting chemistry that might work for a television program. And I started coming up with ideas, the things that excite me the most, and whatever. And each time I came up with something, she sort of looked a little doubtful. She said, "Well, that kind of sounds like biochemistry." And then another one sounded like materials science, and then there was one that was nanotechnology, and another one like pharmaceuticals, another one like forensics, and where was the chemistry? And I went, but it's all chemistry. That's, chemistry is kind of all over the place. And it took me a while to realize what the problem was, is that she was looking for the smells, she was looking for the colors, she was looking for the bangs that so many of us present to the public. Was chemistry over? And the thing is that, on one level, she's kind of right. But chemistry as a discipline hasn't vanished. It's quite the reverse. And it's actually that chemistry has gone on, in a sense, to invade all the other sciences. And, of course, the simple exploratory chemistry where you take, the kind of thing that my kids ask me about. If you take this and you take that and you mix them together, does it go kaboom, right? Well, a lot of that stuff is done, right? We've really mapped it out. We have a very good handle on what reacts with what, and so on. And what that means is that now we've been able to go well beyond that, and we can design complex devices, right? Solar cells, catalysts, microfluidics, polymers, detectors, active coatings, that sort of thing. And that's without there being one of Mark Lithgow's favorite explosions, right? And having said that, though, I would just like to draw your attention to an amazing paper that came out in Nature Chemistry last week. And really, it was just so startling that I felt I had to tell you about it. And this is, it was really describing what happens if you lob sodium or potassium, or better still, the liquid, terrifying liquid alloy, NaC, sodium potassium, into water. And the answer is, well, yeah, kaboom. But what these guys did, and this was a group in the Czech Republic, they did what we did, in fact, Jim and I and Helen Thomas did when we made Chemistry of Volatile History, which was to actually film the process with a high-speed camera, right? And here are the screen caps courtesy of Nature Chemistry, and I'm very grateful to Stuart Cantrell for telling me that this constitutes fair use, and so the Royal Society isn't going to be sued for the fact that we're webcasting this. Anyway, I want you to look closely at the images, and you can see here is the drop coming down, and you can see clearly kaboom, yeah? But I want you to look very closely at this, because if you look, you'll see something remarkable here, and that's blue. And that blue color is telling us that there are electrons which have left the metal. These are the rats leaving the sinking ship. And what they do is they actually get solvated, they get surrounded by water, right? And just for an instant. But the result is that the drop is left with a positive charge. And that positive charge starts being huge, and it's so big, in fact, that it overcomes the surface tension. You get a Rayleigh instability, and suddenly our drop turns into a hedgehog. Look at it. There are these spikes which get fired out from the droplet at 10 kilometers per second. I mean, it's a shocking speed. And the drop basically blows itself to pieces, not by the old explanation, right, that the hydrogen ignites and so on, but by this Coulombic explosion, this electrostatic explosion, which blows it to pieces. And what is so fantastic is that it's a whole new look at a real classic that everyone's done in school and that we thought we knew everything about. Now, when I say that chemistry has changed, one of the things that you have to realize about this paper is that if you were, in fact, to scroll down a little bit more, then you would find something else. And what you would find would be computation. You would find computational results. And this is really important because chemistry departments today no longer just house, sort of minions with glassware, right, and solutions, but they actually house server farms, right? And computation underpins, right, a hell of a lot of chemistry. And it's hard stuff, right? There's kind of classical and quantum mechanics, and in many cases there's relativistic stuff which gets put in there. This isn't kids play. This is really difficult stuff, and it's stuff that the general public don't often hear about. And the reason that we use them is because they work. Now, this is a big story across the whole of science. Sometimes people talk about big data, but it's not just that. It's actually doing simulations and modeling. And there's a really important general point about science, and that is that you ignore simulations and models at your peril, right? And we use them because they really work. But as I said, chemistry has changed also because it has invaded the impact that it's had on other disciplines. And everywhere you look across the world of science, you'll see the tools of chemistry being used. Whether you talk to an electronic engineer, a nanotechnologist, somebody in the world of genomics or metabolomics or the other bolomics, right, that are out there, oceanography, archaeology, and so on, people are doing sort of chemical processes. And so you need to have an inkling of that world of atoms and molecules, of structure and bonding. And I started to ask myself, when did this happen? And as Russell mentioned, I have this column called Classic Kit, which is really looking at chemistry through the prism of apparatus. And it's gone through, I think now it's 91 or something episodes, and I just can't believe that it's a gift that keeps on driving me crazy every month. But looking back over these individual devices, there's one that really stands out for me. And and let me see if my slides are in the right order, is this one, and that is Michael Tsvet's column. And Michael Tsvet was an obscure Russian botanist, and he was interested in taking apart the machinery of photosynthesis. And what he did was he ground up some leaves, and he added some solvent, and then he poured it down this little tube on which he had some powdered chalk. And what he found, to his complete amazement, was that he got a series of colors that came out of this. And what this is, in essence, is really setting up molecules in a kind of race where you sort of blow the whistle here, you fire the gun, they all start running down the track, and some, which are stickier, right, go more slowly, and the less sticky ones kind of run through to the end. And what it allows us to do is to chop the world up into its components. And there are a myriad variations on this. Now, I think if you haven't done chromatography, then you've really missed something big time. And what I'd like to do is to illustrate it with 1 minute from a film made by a friend of mine recently, and that's Alam Shah at the Royal Institution. And I just want to show it to you, just, I think, 60 seconds.
Peg it on here. Right. What's happening?
It's growing bigger.
It's going bigger. And what else is happening to the...
Oh! It's going blue.
It's going blue, isn't it?
Yeah, it's going blue.
Is there anything else apart from the blue you can see?
Black. I can see light pink.
Light pink. So we started off with a black dot, and the water's gone through the black dot.
And there you can see chromatography in action. And chromatography is, one might present it to children, but the principle is the same. Now, the reason I've shown you this is because I think this project is not the usual attempt to film cool stuff, but it's an ambitious project to introduce children and their parents to the idea of asking questions. And, it's going beyond just that wow factor. And as Paul Nurse said in The Guardian a couple of days ago, finding out things for yourself is the very heart of science. And especially when we're talking to children, it's incredibly important not only to draw their attention to the marvelous wonder of things that go unnoticed every day, but also to get them to ask questions and to continue to do so. And for the past few years, my wife Amelia and I have been involved in the Lab 13 project, and which I hasten to add was not my idea, but which is represented tonight by Carol Kenrick from Gillespie Primary School. And it's a project to put a messy play space, a lab, in a school, where children can ask their own questions and try to find out answers for themselves playfully. And I think it's an amazing project that has important ramifications across education. And what it does is it raises questions that we should legitimately be asking about how we train our own undergraduates, even at university. Where I think often there's not enough play and not enough exploration until finally they get to their final year and they do a research project, and it's delightful to see Peter Scott nodding, sort of, because I think we're on the same wavelength on this. Sometimes we focus too much on a narrow learning objective, and the students are kind of hammering through a lab manual, following slavishly, and there isn't enough time to get something, I know, woollier, but possibly something deeper. And it's hard to reconcile with the way universities are built. But anyway, to return to the main thread. If we're going to present chemistry to the public better, how are we going to do this? And I think it's incredibly important for us to stop trying to impress people with shock and awe, right? And start realizing what the physicists and the biologists have been doing for years. I mean, my predecessor, Brian Cox, has an almost uncanny ability to talk to you about physics and astronomy in a way which makes it sound almost like a mystical quest, right? He sometimes sounds like Pope Urban II in Clermont-Ferrand, right? Calling people to go to Jerusalem or something. But it's really finding those big questions that have an almost religious resonance. And I think as chemists, sometimes I think we focus too much on applications, on the wonders of plastics, a miracle drug, or the marvels of fluorescence. But is this enough? It's kind of applied, it's relevant, it connects with people's lives. But I worry that it sounds a little worthy sometimes, right? It isn't visionary. It doesn't soar into the realms of existential mystery. And you know, there's kind of a UK-British class thing here, right? The physicists are, in the old parlance these days, land, right? They're posh. You'd marry your son or your daughter to them, and they use the front entrance. Whereas we chemists, right, we focus on our applications and our devices, and we wear our filthy lab coats, right? We have to use the tradesman's entrance because nobody actually considers us to be quite classy enough to come in through the front door. So maybe what I should do is to show you something that I think is really mysterious and that really caught my attention a few months ago. And I saw it in Chapel Market in Islington, and it just stopped me in my tracks. It's a beet. And some of you think this is funny. Here I thought I was in front of the geekiest audience in the UK, and I'm disappointed because there obviously aren't very many vegetable spotters. Which is a bit of a shame. Anyway, this is called a candy stripe beet, and they're very easy to grow, apparently. But you know, the question is, how did the stripes get there? And this is a question that Darcy Thompson was asking way back in 1917 when he wrote On Growth and Form. And of course, the question is morphogenesis, right? Where does structure and shape come from in biology, which are some of the deepest questions of our time, and that you know, loads of people I know here in the audience are kind of working on. And so, I mean, I know that that some of this is going to trivialize things a little bit. But what I want to draw your attention to is really the way in which perhaps chemistry can shed insights on this and to start to give us an idea of some of the complexity that's involved. And so what I want to do is simply to start by talking about how people perceive chemistry to be. And so, you know, what is chemistry for the man in the street? Well, it's a guy wearing funny glasses, usually a lab coat and so on. It was a piece of funny glassware that was designed, by the way, by Emil Erlenmeyer in 1861. Right? And it's filled with a substance called A, right? And what you do is you do a reaction, right? Where you go A and then you add B, right? We're not always the most imaginative in our naming. But you take A and B, and of course, when you're going to do that, what you're going to do is you're going to write an equation, right? A plus B, and then there's an arrow, and here they're products. C plus D. And it does look a little bit dry, doesn't it? It's a bit abstract. Sounds a bit like bean counting, really. You know, the equation actually dates from the end of the 18th and the beginning of the 19th century when chemists, you know, the only thing they could do was weigh how much they started with and how much they ended up with, and they felt like second-class citizens to the physicists who were using maths. And so they came up with their own very sort of simple things, and that was the equation. So anyway, let's just do this, and let's mix them together and see what happens. And so when we do that, right, a miracle happens, right? This is magic, yes. Now, you know, I know that the chemists are sitting there and they're saying, you know, I just can't believe that you've done something, you know, you've brought me all this way just to see you turn phenolphthalein pink. But there's something really important here, and that is that, you know, where was the chemistry in all that? You know, we saw this thing, but remember that the chemistry is not in the A plus B or in the C plus D, because let's face it, this is a story. What we've done is we've told the chemical story. We've started at the beginning, and we've ended at the end, and you know what? You don't go. You don't open time out, and you're not satisfied with the idea that husband and wife kill king, they get their comeuppance. No, you go to the National and you see Macbeth. and A plus B, arrow C plus D, it's in the arrow that the plot development is. That's where the chemistry is. And we kind of tuck it away all in there. That's where the plot is. And that's something that I think we have to really get across. Now, the other thing is that although I know it seemed a little bit trivial, this reaction, right, typifies all reactions. Notice that it's not going anywhere. It's not doing anything. It's finished. It's dead. It has ceased to be. It is an chemical reaction. Why is that? Well, it's reached equilibrium. And equilibrium, remember, although it's kind of important we all learn about it, it's the most boring place you can be because it's the end. It's chemical death, right? Why has that thing got to equilibrium? And for this, we really need to draw on the insights of one of the great fathers of modern chemistry and modern quantitative chemistry, and that's Avante Irenaeus. And Irenaeus is really important, and he's really important not just to chemists, but also because he was the first person to make a quantitative estimate. Sorry, and these are in the wrong order too. God, I'm having a bad evening. The first person to make a quantitative estimate of the climate sensitivity, and he calculated that the Earth would get 4 degrees warmer if you doubled CO2. And actually, interestingly, considering he did that around 1910, right? You know, he's only at the top end of the IPCC's best estimates. So he wasn't doing too badly. But the thing that he did for chemistry was to introduce the idea of there being a chemistry landscape, is that when you mix things together, our molecules move through that landscape. And this picture is really for Ramid Sabar, with whom I went here last summer. But you can think of a chemical reaction as starting up in the mountains, and what happens is that the molecules traverse that energy landscape, and what they do is they're going down in energy towards the sea. And the sea is where equilibrium lies, right? And so all chemical reactions do that. And I have, of course, managed to get away from my script, which is exactly what I was afraid of. But what I want you to do is to keep an eye on this reaction here. Because now we're going to go for something a little bit less trivial, and I've mixed together various reagents. The details don't actually matter. But this was a reaction that was first discovered, first observed by a Russian chemist called Boris Beluzov. And Beluzov was interested in that central sort of biochemical cycle, the citric acid cycle. And so he started doing some experiments in which he tried to oxidize some carboxylic acids and so on. And what he saw was something really, really surprising. And because I've got my timing slightly wrong, this may take a moment to kick off. But what I'm going to do is I'm actually going to put an indicator into this mixture. And the indicator contains a little bit of iron, and that iron is going to act as a reporter for us on what's actually happening in the solution. And what I'm hoping you're going to see in a moment, right, and this is always fraught with danger when you do stuff live, is that the reaction is going to start changing color. And it's going to start changing color in a very peculiar way. It's going to go from this rather nice green. In a moment, you're going to actually see it go red. And when it goes red, it's going to sit there for a bit, and then it's going to switch back, and it's going to go green or blue again. And then it's going to switch back, and it's going to go red. And you might be tempted to think, hang on a second, is that a reaction that can't make up its mind? And the real tragedy of Beluzov was the fact that he couldn't get across an explanation which would satisfy the referees, and the referees thought he was raving, that such a thing was completely impossible. And Beluzov, in fact, stopped doing chemistry. I mean, he just got so depressed at the referees' comments that he kind of gave up. But what he'd observed was actually real. And I'm just going to add a little bit more. Ooh, there it's gone green, you see. And so this thing is going to kind of keep flipping back and forth between these colors. And the thing is that the referees thought that what he was saying was that this reaction went down to the bottom like this, and then suddenly, halfway along, kind of changed his mind and went back up to the top. And this would be a little bit like you going tobogganing, right? And suddenly your toboggan changes his mind and goes back up to the top, which is clearly absurd. But actually, this reaction is much, much more interesting than that. Because this is a really rare example of where you can actually see the arrow in action. you can actually see the descent from the top and the bottom of the hill. It's a little bit like sitting, right, at your chalet. You've got your binoculars, and you're watching a skier come down through the landscape, through powder snow, doing carving turns, red, blue, red, blue. This thing is inexorably going to equilibrium, right? But we can actually see that the path of true chemistry, whatever. Let me just show you a mechanical analog of this, and this is something I've stolen from my children, and thank you for lending it. No, for letting me take it away. Anyway, I'm just going to put them up at the top, and I want you to show what happens. Want you to see what happens. So notice that the duck goes down the hill. Yeah? He's going inexorably to his death. That's equilibrium, the bottom, yeah? But there's a kind of built-in mechanism which will, oh, he's dead. There's a built-in mechanism that allows him to walk down. And so the question is, how do you set up something like this so that it will give those amazing changes so you can see that path? Okay, so to do this, I'm going to set up a second one of these oscillators, right? And this is one which is going to generate iodine. So you'll actually see iodine being produced. Now iodine is yellow, and so you'll see the telltale yellow color within a few seconds of my mixing it. Or not. Many years ago, something similar happened. If it starts, let me know. But something similar happened to me. And David Phillips, who's a previous winner of this prize, he was in the audience, and he came up to me at the end, and he said something which changed my life. He said, "You should always have something fail in your lectures." And I went, "What?" And he said, "Yeah, because that way they'll know it's not television." It's great. That one was for you, Helen. Now, okay, so we can't do it. We're going to resort, in fact, to television. And what worries me is that a virus has appeared on my Mac, which is annoying. Let me just see if I can get a video up. No, wrong one. Okay, here we are. So here is what was supposed to happen. Okay, and I'm sorry, let me just turn the sound. The sound should be off. Okay, and now it's stopped. Okay, it's stirring, and you can see the iodine appear, and then it's going to disappear. Right, it's going to appear, and it's going to disappear. And then I'm going to add an indicator. So there's the iodine, and then the iodine disappears. So it's going up, and then the concentration comes down. Concentration goes up and comes down. And in a moment, you'll see my hands as I add a little bit of indicator. And Peter, please don't comment on the fact that I've got gloves. I don't know why that happened. It was a momentary aberration. Anyway, you'll see we got the indicator, and that goes blue, right? And then it's going to disappear again. And this is magic of a high order. And the question is, how can you set that up? Because we've clearly got concentrations of different things going up and down. Now, the key thing to recognize is that these are not the products that you're seeing. What you're actually seeing are intermediates. And what we need to do is to come up with an analogy which might explain this. Now, these flasks are contained, and a little bit like this room, we can imagine this room to be out in the Cotswolds or something, and we've got a green field, and we've got carrots down at the end, and we're going to put in a couple of rabbits. And the analogy is not as far-fetched as you might think. So we're going to put in one male, one female. What happens? Oh, look, and we're not going to spend too much time on this. I'm not a biologist, so we're going to cut the chase. You're going to get more rabbits, yeah? And so all I'm going to do is I'm going to plot. I'm no graphics whiz, so I haven't got fantastic Hans Rosling-like pictures to give you. No, we're going to do it as interpretive dance, right? Here is the population axis over here, and here is time increasing inexorably horizontally. Okay, so we start here, right? This is t equals 0, where we put in the 2 rabbits. There's a bit of an induction period, and then what happens is you get more rabbits, right? Fine, that's great. Of course, the fact that you have more rabbits means you get more dates. And if you get more dates, then you get more rabbits. And you get more rabbits, and the thing kind of takes off like this. Now, this is really important because it's totally parallel to chemistry. The higher the concentration of rabbits, the higher the concentration of the reagents, the faster the reaction's going to go. And this thing leads to a kind of positive feedback. This is what we call autocatalysis, where the thing takes off, and basically you've got Australia. There's rabbits seething everywhere. What are we going to do? Well, I think what we need are natural methods natural population control methods. We're going to get ourselves 2 foxes, one male, one female. We put them into the enclosure. Well, natural methods we know are cuddly and friendly, and anyway. Here we are. This is TF, the fox time, right? We put in the 2 foxes. What happens? Well, the foxes go on a date. Needless to say, they eat rabbit. You get more foxes after a bit. That gives you more foxes. The fox population starts to rise. But of course, as the fox population rises, you're eating rabbits. And so eventually you're going to get to the point where the rabbit population drops. The fox population is going to now fall, and the 2 things are out of sync. And suddenly you have a model which allows you to get these kinds of oscillations. Now, I've simplified hugely, and I apologize to the professionals in the audience who really know about this stuff. But the interesting thing is that the original population models that people like Lotka and Volterra came up with at the beginning of the 20th century were actually, in many ways, using mathematics, which is the same as chemical mathematics, as the rates of chemical reactions. And the parallels between the 2 were really kind of intriguing and have remained. The only thing is we've changed the symbols to protect the innocent. Now, you'll remember, of course, the beat. And some of you are wondering, well, what about the beat? I mean, what happened to that? And the beat is important. But I want to draw your attention to something. Let's just get the picture of the beat up there, because there's something I'd like you to notice about the beat, if I can get to it. And that is the fact that unlike these bottles, right, the beet is not stirred. It's not even shaken. It's sitting there quite happily, whereas these things are mixed. And of course, if I take a beet and I drop it into a blender, or a rabbit, perhaps together, right, and I press the button, I get soup, but the beet doesn't work as it's supposed to anymore, nor does the rabbit. And this is really kind of interesting, and it's an insight that was actually sort of dreamt up by Alan Turing. And in 1952, he published a famous paper where he pointed out that if you did in fact have chemical reactions which were doing this feedback stuff, then if you didn't stir them, then if you included just one extra factor, and that factor was diffusion, then something interesting would happen. And he wrote his famous reaction diffusion equation. Here it is, right, which includes a diffusion term in the middle, right, and the rates of the reaction on the right-hand side. And he started scribbling in his notebook solutions to that equation. So what I'm going to do is I'm going to take this reaction here, and instead of stirring it, I'm going to put it in a Petri dish. And I'm very, very grateful to Susie Arnott, who is in the audience this evening and who a few years ago filmed this as a time lapse. And it's absolutely brilliant, and I'm so grateful to her for letting me use this. Anyway, here we go. In the Petri dish, we've mixed it up, right? So everything's uniform. Look at it. Look, there's a pattern. In fact, look, there are kind of rings, there are spots, there are even some spirals there. And the astonishing thing is that these spirals appear essentially out of nowhere, right? Let me just show them to you again. And now what I want you to do is I want you to look very closely at that thing on the right. And, you know, oddly enough, if we just skip Alan Turing for a second, it looks weirdly like that beat. In other words, it is possible to generate pattern without having an explicit program. Is that this is a pattern which emerges spontaneously from the dynamics of the system, right? That kind of takes care of itself. And, you know, what's astonishing is that the pattern kind of builds and you get variance on it, the spots, the spirals, that kind of thing. Eventually, if we let this thing go, we're going to get to, sorry, I don't know why this is misbehaving like this. We're going to get to, no, it will not go, there we go. We're going to get to kind of a plumber's nightmare. But what's really interesting is that simple chemical reactions can start to give us tremendous insights. And of course, nothing is quite so simple. That beet is a little bit more complicated than my Petri dish. But I think the take-home message is that, the complexity that you see there is actually related to the fact that, chemistry is also complex and difficult. There's no escaping it. But is that different from any of the other sciences? I mean, it's not like genetics, immunology, glaciology, and medical imaging are that trivial and easy, far from it. And contrary to what Mr. Monckton and that interpreter of interpretation, James Delingpole, believe, climate science is pretty complicated too. All of the sciences are. But the thing that we chemists need to do is to bring out why chemistry is so deep and so important and what makes the study of chemistry so worthwhile. It's not the bangs, it's not the colors, it's not even the myriad applications. It's that, for example, chemistry provides a link between the animate and the inanimate world, between the mineral and the organic. And the soaring ambition of the Philae Rosetta mission is its search for answers to one of the deepest questions of all, and that's the origin of life, right? And that at its heart, is a chemical question. And to do this, it has on board, right, a small, perfectly formed chemistry lab. And some would argue that life is impossible without a creator, given that the world of atomic and molecular phenomena are random. And they quote Einstein, of course, which is what you always do when you want to sound posh, and they say God doesn't play dice. But the answer that I think chemistry gives us is that the universe is unquestionably a huge molecular crapshoot. But it's a crapshoot where the dice are very heavily loaded. And I think what we will probably find, what we'll probably start to see, is that not only, as we know, is pattern deeply embedded in our universe, but that perhaps, and just perhaps, life is a kind of inevitable result of chemistry taking place on that steep energy slope, right, provided by our sun. And it's our job, not just as chemists, but as scientists, to unravel the processes that give us the rich world we see around us. And to those who missed out on this fascinating journey, we've got to tell them what it is that we've learned along the way and what they, poor buggers, have actually missed. And I have one more thing which might undermine everything, because on my script it says, and yet. You know what, maybe I should get Russell to, why don't we do the questions, and then we'll just sneak something in the last minute or two, because I know I've overshot, but I want to be cheeky with the last little bit. So thank you very much.
Well, Quentin Cooper said there was a 99% chance of enlightenment and 1% chance of being burnt alive. We haven't been burnt alive.
Not yet.
And we've not yet. We've had 100% enlightenment. We have time for a few questions. There are a couple of roving microphones. Anybody like to ask the first question?
I'm just a monkey.
Any questions emerging? I can't believe that there's no questions.
Oh, good. So relieved. This gives me more time to mess around.
There we go, over there.
What's the next greatest chemical discovery?
What is the next greatest chemical discovery? Well, I think one of the greatest challenges is really to unravel the origin of life. I mean, I think that really is huge, but it's not going to come just from the chemists, right? It's going to come from all kinds of different directions. But there are so many questions that remain to be addressed. The origin of chirality on Earth, those kinds of things. They're really important, they're really deep. And I think, I guess the point I'm trying to get across is that sometimes we chemists don't talk about these big questions enough to the general public. And it's a real quest to get to that.
Do you think children get enough experimental chemistry at school?
So the question is, do children get enough experimental chemistry at school? And I mean, I think I would ask the same question of our undergraduates, right? I think that we've tended to whittle stuff away, and we've tended to narrow it down and to package it up and to put it into boxes because the way we assess things has become more and more formulaic. And I worry a lot, not about the fact that there isn't enough practical stuff. There is all this discussion about the recent decision by Ofqual to possibly remove a practical component from some of the A-levels. But what worries me is that there isn't enough of the process of science. There may be the tools, but how do you think like a scientist? How do you solve the problem? And of course, that's much harder to assess if what we want is a rigid marking scheme. And you know what? In these times when we've got a million things to do, the last thing you want to have to do is to start sitting there kind of scratching your head about, what you want is to be able to say, yes, this is right. You got it. No, wrong. And we know that when you're actually out doing real science, then you're never quite so sure.
And of course, the iodine experiment failed. Why did it fail?
Because it was 2 bottles of tap water. I confess. I'm sorry. It was a total con.
Oh.
I had to come clean. But the thing is that I know that there were so many people in the audience who were expecting me to screw up that I thought I'd throw them that bone.
There's a question at the back.
Thanks very much, Andrea. Andrea taught me as an undergraduate chemist at UCL several years ago, and he's fantastic, even teaching undergraduate chemistry. But he also teaches undergraduate biologists chemistry. And the question that I have is, what have you found by spreading the chemistry to those other disciplines? What have you found out about chemistry that most interests you, or other people's perception of the stuff that they learn?
For me, when I took that course on, and this is a course called Chemistry for Biologists, it's one of the larger courses in the university, and I've run it for a very, very long time. And when I was first asked to run it, I really thought, oh my God, what could be possibly worse than to trying to teach chemistry to people who are absolutely desperate to get away from it, who thought that they had escaped the clutches of chemistry, right, forever. But actually, I think the reverse is true, is that for me it has become this incredible, exciting challenge, is how do you convince life scientists that actually that foundation of knowledge is crucial, because without it, they can't really do an awful lot of what is called biology these days. And I mean, I'm sure you'd agree, in your lab, a hell of a lot of the tools that you use, the fluorescence, all these things, these are basically little devices that were built by chemists over the years as neat chemical curiosities, and which then have slowly spread out into the other fields. So I've learned a lot, I think, about maybe how to talk to life sciences and make the chemistry sound more relevant to them, and not simply a dry set of equations.
One last question. Gentleman over there.
Thank you, Andrea. Very entertaining. I hesitate to remind you of the title of your talk. Is chemistry really so difficult? And I didn't get the answer. Was it yes or was it no?
I think the answer is definitely yes. But it is yes in the same way as physics is difficult, genetics is difficult, immunology is different, nanoscience is difficult. Sorry, not different. They are different. But yes, unquestionably, right? But one of the things is that I think we also make it look more difficult and more daunting by the way we present it.
Andrea, there's a dilemma now.
Okay.
You wanted your last experiment. Now, do you want it before
It's
or after?
not an experiment.
Okay. Do you want it before or after the check? Your call.
Let's do it after.
Okay,
We'll do it
there's a sensible amount.
because
right.
people might want to run away.
Okay. Well, I'm honoured to be able to present you with both a medal and a cheque and a scroll for the Faraday Lecture. Many, many congratulations.
Thank you. Thank you very much, Russell. Wow, it's amazing.
Amazing.
Wow.
Congratulations.
There it is. Wow, it's amazing. I think one of the things that I'm going to have to do now is two things. First of all, go to the Institute of Making, where I'm going to have to get the pillar drill that you guys trained me up on the other day and drill a little hole in the middle, because now I've got to change my image. And then I'm going to wear the big medallion right up front, right, so that I can, yeah.
Okay, so you have just a few more moments,
Just a few more moments.
and then we'll wrap things up.
And yet, for all this highbrow sort of intellectual stuff that I've talked about, there's no doubt that chemistry has sights and smells, sounds and light and thrills, Feuer und Flamme, Schall und Rauch, that no other discipline can match. And so, I've really got to end off with one of the great 19th century party pieces. And before I get into trouble with the authorities, with my head of department, who is totally paranoid and is watching this from New Zealand, and who knows that we're all going to die. I'm going to wear a lab coat, which smells suitable. It's great. And what I'm going to do is I just want to remind you, do you remember when you were in school and you did experiments in test tubes? Something that Philip has written so eloquently about, the origin of the test tube. Remember those? How big were they? Yeah, that size. Okay, so what I'm going to do is I'm going to pull out my official professorial scale test tube. Because, I feel it's really important to give you an idea of what it is that, the senior chemistry professors like David Phillips, Martin Polikoff, Malcolm Green, Robin Clark have spent their lives doing, yeah? And you take a look, it's a very nice test tube. In fact, I'm very grateful to Reese Bramley, who made it for me, and Dixon Glass, emblazoned on the front. But this is going to be the reaction of nitric oxide, which is in the tube. For the nerds amongst you, this is Biochemical Molecule of the Year, 1992. Small, diatomic. And what we're going to do is we're going to put into it carbon disulfide. And carbon disulfide is an exceptionally smelly molecule. And so we're going to drop in about 9 mils of it up at the top. And if I can get the stopper off. And a little bit of brown color, which is rather attractive, but something I want to avoid. There was then a pressure buildup. It's not going to do what that one did, okay? So you can relax, but let's just release the pressure for, oof. Yeah, it smells. And if you can't tell who the chemists in the audience are, right, then what I want you to do is to watch, because this is what some of the experimental chemists are doing all day, right? It's this kind of thing. And you'll be able to recognize the chemists in the audience by their absolutely outstanding physiques. Anyway, this thing is loaded. And we're kind of ready to go. It's still hissing at me. This thing is a little bit of a kind of tiger. Okay, there we are. All right, so the stopper's on the top. And now, of course, because of Irenaeus's chemical landscape, we actually need to give it a little bit of a push. And what I'd like you to do is to imagine yourselves in Switzerland now. We'll need to have the lights down just a bit, right? When I take maybe a little bit further. Maybe a little bit further. And I will say lights out in a moment. But what I want you to do is to imagine yourselves in St. Moritz at the top of the Cresta run with your helmet on, lying down on the sled, looking in terror down the slope. This, too, is chemistry. Thank you very much.
Well, what an extraordinary way to end the evening. Once again, Andrea, thank you so much, and many congratulations for your phenomenal lecture. Thank you again. Cheers.
Thank you.